Hi everyone, I'm Waldi Bauer from the Institute of Organic Chemistry of the University of Erlangen in Germany. And we are here in the NMR department, and behind me, this is our superconducting magnet. The strength is 11.7 Tesla. This is 500 megahertz in the proton frequency. But today I'm not going to talk about chemistry or physics or whatever. I simply want to show you a couple of experiments, simple experiments, so you can see how strong the magnet actually is. And from the good old Deutschmark times, I have kept a couple of coins, which we call in German, and especially in Franconia, Zehnerler. And these coins have an ion core, so they are magnetic, okay? And so you must imagine the magnet, roughly the center of the coil is around here, and the magnet is a non-shielded magnet as opposed to the other ones, which are the modern ones, and it has a stray field, a fringe field. And this field extends out here, it goes vertically and goes back into the magnet again. And just to make you see what happens when I take these magnetic coins and put them inside the magnetic field. So look here, one coin sticks after the other. Next one, the next one, and the next one, and one more. Okay? And the stray field, the fringe field, extends quite large. So I can take the coins and try to move towards you, towards the camera, and let's see what happens when the field will be so weak that these coins will no longer stick together. So today is a good day. I think it's full moon, possibly. So you see, we have a very intense stray field. We can make a different experiment. As I told you, the stray field goes out here, it goes vertically down, and it ends up horizontally inside the magnet again. Now this, what I show you, is a very ordinary office clamp. Anyone has it in his office, his or her office. So I take the clamp and put it on my hand, and you see it stays upright on my hand, and when I lift my hand, it will follow the magnetic lines, like this, okay? I go down with my hand, I go to the bottom, and you see the clamp strictly follows the magnetic lines, which otherwise you wouldn't see. When I let it drop, it will stick to the magnet, which is not harmful by using such a tiny device. But you can imagine when you have large gas bottles, this might be dangerous, and eventually the magnet might quench, and there have been many, many severe accidents in the past. And a last demo, I'd like to show you, this is a plate made of aluminum, and aluminum is non-magnetic. So I can take the plate and put it to the magnet, and you see nothing happens. But whenever I move such a plate in a magnetic field, so-called eddy currents are created in such a material. And we can demonstrate this quite easily when I take the plate and drop it to the floor, like this. Very normal. You see, gravity is working. Okay? But now I take the plate and put it beneath the magnet. Okay? The field goes here and goes into the magnet again. And now watch the plate falling to the ground, and you will see it will fall in slow motion. The reason being the induced eddy currents in this aluminum plate. Now watch what happens. 3, 2, 1. That's the dropping speed, the slow motion dropping of this aluminum plate in the magnetic field, and this is caused by the eddy currents, in German Wirbelströme. Once again, okay, I hope you have enjoyed this short demo of these nice experiments, and let's continue with my lecture. We will start in a couple of seconds. Thank you very much. Welcome everybody to this lecture. Glad to see you. And today I'm going to talk about a topic which is non-normal, in quotes. I guess anyone in the audience knows I'm doing NMR spectroscopy here in the Institute. And this lecture is entitled NMR Meets Musicians. Musicians is a so-called acronym. That means each letter stands for a certain word. And in the end of my talk, I'll tell you what musicians actually means. So I'd like to undertake an acoustical journey to the world of the atomic nuclei. And any one of you has recorded NMR spectra before. Anyone knows what a proton spectrum is, a carbon-13 spectrum, and so on, 2D, NMR, and. But actually, what we can do, we can listen to atomic nuclei. And on the first 2 or 3 slides, I give a brief introduction into NMR because to you it's possibly boring, but people outside might not know about the backgrounds. We have atomic nuclei. And in a magnetic field, of course, anyone knows, atomic nuclei are precessing. They have 2 spin states, either in field direction or against field direction. Anyone knows about that. So the spin is a central term in NMR, and we always visualize that the spins are moving around a certain axis. And the spins themselves, the atomic nucleus, it turns around an axis. Don't be too serious with this picture. This is something which physicists have introduced many years ago. Wolfgang Pauli basically has introduced the term spin. Don't take it too serious. To us, as being chemists, it's a good picture to think about an atomic nucleus to spin around an axis. In real, no one knows if this is really true, because also electrons do have a spin, an electron spin. And when you calculate the whole thing, you will end up with the result that the electron should spin with a speed faster than light. What cannot be, of course. So we, as chemists, we think about spin. The atomic nucleus spins around an axis. That's a good picture. And we call the movement in the magnetic field precession. In German, eine Präzession. So this is a simple picture. I guess anyone knows about that. The atomic nucleus here spins around this cone, basically, in a magnetic field. Right. Here's some text. We try to bring them to resonance. And this is done, or this is achieved by putting in the radio frequency. And that means we have a certain oscillator in our spectrometer, and we can bring the spins to move from up to down. A very simple picture, and we can measure this. And this is called nuclear magnetic resonance. We bring the nuclei to resonance. Okay, so this is the initial picture, and we feed in radio frequency, and we bring the spin to go from up to down, and in addition we create a so-called phase coherence of the spins. That's very crucial, so that the spins are in phase, and they behave like a tiny magnet, basically, inside a coil, and they move inside the coil, and this basically creates a current which is measured with a very high frequency in the end, but we can measure it. And so here's a scheme of an NMR spectrometer, and don't get confused. This looks a little complicated. So the main thing, of course, is the magnet, a very strong magnet, very expensive magnet. We have inside the probe head, we have the sample tube, and we need a lot of devices outside to observe the atomic nuclei. We have to lock, and we have to shim our sample, and. But the same principle is applied in MRI, magnetic resonance imaging. That means I asked the audience, has anyone ever been in an MRI magnet? Not yet? Okay. So you can, you can tell it's a little loud, and the sound, which mostly sounds like boom, 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 and so on. This is nothing but the switching of the gradients. We need field gradients to achieve a picture out of the human body, otherwise it wouldn't work, basically. So the field itself is silent, of course, but the switching of the gradients, this is the noise that we do percept inside the MRI magnet. But the principle is the very same as we apply in analysis of unknown compounds. Okay, but what has NMR to do with music? Right. The precession frequency of the nuclei is very, very high. Our instrument in our institute has the highest field, 500 megahertz, but of course we can't detect directly 500 megahertz. And so what is done inside the spectrometer is a demodulation. And this is the very same principle that is applied when you're listening to a radio. You listen to Antenne Bayern, you listen to Bayern 3, and so on. This is in the audio range that we can hear. The high frequency is demodulated. And we are only interested basically in frequency differences. This is what we measure finally in the end. And these frequency differences can be heard by a human ear. And typically we excite all the nuclei by a radio frequency pulse. They get the phase coherence, and we measure the so-called free induction decay, FID, which is a common phrase in our lab all day long, 100 times at least. Okay, and the FID basically is like a hologram. It contains all the information that the nuclei give us as a response from the excitation. So in principle, you might cut the FID, might cut out a certain piece, and you have still the same information, not so good resolved, but it's possible. A hologram, I think anyone knows what a hologram is. And we read, finally, our spectrum by applying a Fourier transform, finally. And in the final end, you get a spectrum that you can read, which is known to everyone in the audience. So this is the principle. We excite the nuclei. We get the response of the nuclei as a free induction decay. And finally, we can sum up as many FIDs as we want. And finally, we do a single Fourier transform, and we get a spectrum. Very simple. In principle, what we do, what you are currently doing, is the very same. Our human ear is perceiving a time domain signal, but you hear tones. You can judge what is the frequency of my voice, for example. And when we are listening to music, our brain does, on the fly, kind of a Fourier transform. Think about that. Okay, and so when you look, for example, inside an audio studio, you see something like that, and you see signals here, and these signals are acoustic signals, but they look like an NMR FID, basically. And so the idea is, why not listen to NMR signals, to FID signals? And this can be done. You see here, this looks much like an FID. Here's a cutout. This is an audio signal, but it might be as well an NMR FID. Okay, so a couple of years ago, 20 years ago, I thought about that. Okay, Samson FID. We got new spectrometers from the Chigol company 20 years ago, in 1994. And the first thing I did with the 500 megahertz was to open the device and do some soldering inside the device and to plug it here to an amplifier and to loudspeakers. And so it was possible to listen to NMR FIDs. Here's our sample. We get the high frequency, which is demodulated to an intermediate frequency here. It's mixed down, and finally we get kind of a stereo signal, and we can listen to the audio frequency of an NMR FID. That's a basic principle. Okay, here's an example. Acetaldehyde, a very simple compound. And of course, anyone knows about that. The aldehyde proton resonates at roughly 9.8 ppm, and the methyl group at roughly 2.1 ppm. And so we can, of course, assign the signals in the spectrum. And we have a quartet from the coupling of this proton with the 3 neighborhood protons. And of course, one of the blue couples with one purple or pink proton, so we get a doublet upfield, a very simple spectrum. Okay, and actually this is the FID of acetaldehyde. And what we can do, we can basically listen to the FID, and it sounds like that. This is the NMR spectrum of acetaldehyde. The hologram that we do get as the response, as the answer of all the nuclei present in the molecule. You see, this spectrum has been recorded in 1996, very, very old. So these were the beginnings, basically. Okay, we can do something else. We can do a Fourier transform, and we see the spectrum, acetaldehyde, the quartet, and the doublet. Here's an additional TMS. And when we do that, for a zoom out, especially the quartet, when we zoom out the quartet and we excite the quartet, then we get something which looks like this and which sounds like that. So this is the quartet signal of acetaldehyde. And you hear the oscillation in the intensity, and this is nothing but the coupling constant between the aldehyde proton and the methyl group, which is around 2.8 hertz, I guess. Okay, and in this case, I have applied a good shim. So the magnetic field was very homogeneous, and so we get a good spectrum, a very fine quartet, basically here. What we can do, we can detune the shim. This is very easily done by detuning a knob on the spectrometer, and then we get an FID which looks like that. So the shim is now poor, and you can hear it. The decay is much more rapid, okay? And so basically what I'm doing presently, I always listen to my signals, to my FIDs, and before I see something on the screen, I can make a judge, is the spectrum good or not? And I can, in principle, tell where are the signals in the spectrum. So basically, I'm doing the Fourier analysis in my brain with some experience, of course. So when we do a Fourier transform of this bad shimmed signal, we get something like that. This is nasty, as anyone can see. All right. Now, for the true experts, I have an experiment. This is a 2D experiment, and we have different FIDs, real, imaginary, and the whole thing is recorded by using a so-called phase cycling. And when you're listening carefully, at least those who are sitting in the middle might be able to listen to the phase shifting of the pulses. This is the very same when you have a loudspeaker and you plug it reverse, you get a different sound. And the same can be heard from an experiment. This is the phase cycling of the whole experiment, 16 times in this case. We have 3 pulses, 1 acquisition period. And when you carefully listen, you might possibly, hopefully, hear the phase reversing of the signal. Did you note it? Okay, fine. Now, there are, of course, different experiments. This is a pulsed field gradient experiment that I've recorded many years ago. And you see, in principle, the build-up of a so-called gradient echo. And this sounds quite weird, as I can tell. Also an FID. Okay, we can do something different. So this is just the spectrum of the FID that you have listened to. Okay, we can do something different. We can record solid-state NMR spectra, of course. And solids are much, much harder to realize in NMR than solution-state spectra. And so you see here are the parameters, and the acquisition time is only 41 milliseconds. So this FID, of course, decays very, very rapidly. So basically, anything is lost at this point. And as a consequence, we get normally broad lines in a solid-state NMR spectrum. But nonetheless, we can listen to this FID. It sounds like a shot of a gun. Oh, sorry. So this is the hologram, the FID, of a solid-state spectrum, in this case hexamethylbenzene. And when we Fourier transform the whole thing, we get the spectrum, nice looking, the 6 metal groups, and this is the isotropic chemical shift of the carbons of the aromatic ring, and these are spinning sidebands. Okay. Before we record a spectrum, normally we are looking for the log signal, because we have a solvent which contains deuterium, normally. The typical solvent that we are using is C-diesel-3 deuterochloroform. And actually we have an additional oscillator in a spectrometer which produces the frequency of deuterium, and we can see the deuterium on the screen. And we adjust normally this signal to the middle, and then we can push a button which reads log. Okay, but this signal also can be heard. And it sounds like this. Note, the frequency is very low here, and it becomes higher, 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 and so on. And then the whole thing is repeated a couple of times. And this now sounds like this. So this is the signal of deuterium of a typical NMR solvent. Okay. The next question. Oh yeah, that's the signal, and these are called wiggles, by the way. The next question I put to myself 20 years ago. When we can hear NMR signals, is it possible to listen to them in the way that we have learned just right now, and to vary some frequencies, and to put, finally, music out of an NMR sample? Okay. Yes, it is possible. And I have tested many, many compounds, and finally, I found out the best thing is to take a compound which has only one single signal in the spectrum. And of course, acetone is the compound of choice. And the only thing, the reference frequency must be shifted. The absolute frequency of acetone is always the same at a given magnetic field. But when we shift the reference, we might get various differences, and these differences create different tones. So this is a simple spectrum of acetone, and here is, in this case, the carrier frequency, which is shifted in subsequent experiments. And in this case, the frequency, or the frequency difference between the absolute frequency of acetone and the absolute carrier frequency, this difference is 540 hertz. Okay. So we must just move the carrier frequency, and then we get a melody. And the melody might sound like this. Okay, very simple, I admit, but it works. So we can play music by using a very expensive NMR spectrometer. And now this is the sum FID of the melody that we've just heard of Händchen Klein in German. And what we can do in addition, we can make a Fourier transform of this summed up FID, and we get a spectrum, and all the signals are acetone, but the difference varies. And so we have the individual tones. It's a mirror image to a piano because the lowest tone is on the right side, the highest tone on the left. Dum, 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 dum. Okay? And what was amazing to me, actually, is the following observation. This is the quint. This is the bass tone, okay, the prime. This is the quint. And the quint is the most abundant tone in the song. And the prime, the bass tune, is the least abundant tone. And after I had realized this, I checked a couple of children's songs, and in most of the children's songs it's the very same, for whatever reason. The quint is the most abundant tone. I don't know why. Okay. But now, another melody which you might know, which can be played by NMR, is this one. Okay. So the problem is these two melodies that I've played, Händchen Klein and the American anthem, were monophonic, only single tones successively. And the idea was, a little later, can we also play polyphonic melodies? And the idea was we can use broken chords. That means we have to resolve a chord which normally sounds simultaneously into a sound which is like on a guitar. When you are playing a guitar, you are hitting the strings string by string, basically. Okay. And the same can be done with NMR. And anyone in the audience who has birthday today? Okay. All right. Yesterday, a very important person had birthday. Okay. I show you the pulse program of what you heard of Happy Birthday to You. So you see, it has been done in 20 years ago, 1994. And the first thing that we have to do, we have to define the frequencies, and then we have to calculate the different frequencies, which is shown here. And the whole thing is very elaborate, to be honest. And so you see many durations, we have delays, and we have pulses, we acquire, that means we open up the receiver, we record the FID. And in this special case, you see F5 means the quint. F6 is the sixth, the quint again, the octave, and the septime. Da, 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 da. This is what's written here. But the chords are some tones which appear in advance. That means da 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 da. This is the pulse program of the beginning of Happy Birthday. And this continues, of course, a huge page, basically. Yeah. The following sample, you should keep in mind, this has not been ever played on a real instrument. Only atomic nuclei. I'm dealing only with atomic nuclei. And this is a song which was the most elaborate one. And possibly some of you know the movie, the very famous movie, Dr. Zhivago, which has been released, I guess, in 1965 or so. Very famous actors, Omar Sharif, Julie Christie, and a very, very famous movie. And the melody, I guess, is known to anyone. Okay, only NMR tones, and to be honest, it took me a long, long time to program all this. And so the source code of this melody looks like this. So we start with all the individual frequencies, which have to be basically typed by hand. There's little to do with copy-paste. And this was done in 1996. A long time ago. And this continues very, very long. And finally, we end up with a total of 711 individual tones. I guess it was 4 or 5 days which I needed for the programming of this song. And at that stage, 18 years ago, I decided to quit the whole thing because the programming is so elaborate and time demanding. So I left it for a while, but in 2008, that means 12 years later, I thought about, okay, what about playing drums on an NMR spectrometer? And the reason being, I played drums myself in a band, so this is my band. You see, I'm sitting here on the drums. And I thought about, what about performing a drum solo, a short drum solo, by the old way of programming a song on the NMR spectrometer. So here we go. But keep in mind, anything you will be hearing is a very tiny single drop of acetone, nothing else. Okay, let's go. Okay, it works. Single drop of acetone. Now this is, in the end, the Fourier transformed spectrum of the drum solo. Again, keep in mind, each signal that you see is acetone. It's just the carrier frequency that has been shifted. And so we have the lowest tone. Okay, the acquisition time is quite short because drum sounds are quite short inherently. And so this is the bass drum, and we have the hi-hat, and we have the snare drum, we have the high tom, we have the middle tom-tom, and we have the floor tom. And the final ping of the triangle that you've heard, it's this tiny signal here. Okay, so this was in 2008. And then I left it for a while. Again, the pulse sequence of this drum solo, in quotes, we have to define what is the bass drum, the snare drum, the hi-hat, the high tom, the mid tom, floor tom, and the ping in the final end. And these frequencies, again, have to be calculated, which is done here in the parts program, and then the whole thing starts. And so we have, for example, here, bass drum, hi-hat, bass drum, hi-hat, snare drum, hi-hat, hi-hat. And this might sound like this. This is what you see here. And of course, to create a whole drum solo, this extends many, many, many pages more. Okay, the drawback until now, all these songs that I've played, they had to be programmed on the spectrometer by using the pulse editor. A very tedious task, to be honest. And it took me a long time to realize, can we do this in a better way? Of course, it would be much more simple to have a keyboard and play the NMR tones by using a keyboard. And this is actually possible, but it took me a long time, and it was only in summer last year that I was able to realize all this. And now what we can do. First of all, I show you a movie, which is not NMR music, which is a movie, a trailer, a video trailer by Phil Collins, a very famous movie called Against All Odds. And I'd like to watch the movie.
Just let you walk away, just let you leave without a trace. When I stand here taking every breath with you, ooh, you're the only one who really knew me at all. How can you just walk away from me when all I can do is watch you? We shared the laughter and the pain, and even shared the tears. You're the only one who really knew me at all. So take a look at me now. There's just an empty space, and there's nothing left here to remind me. Just a man. Just make you turn around and see me cry. There's so much I need to say to you, so many reasons why. You're the only one who really knew me at all. So take a look at me now. Well, there's just an empty space. There's nothing left here to remind me, just a memory of your face. Now take a look at me now, 'cause there's just an empty space. But to wait for you is all I can do, and that's what I've got to face. Take a good look at me now, 'cause you coming back to me is against all odds. It's the chance I've got to take. Take a look at me now.
Okay, a nice, beautiful song that even Andreas Hirsch and I are playing occasionally. And, okay, you've seen it. Okay. And my idea was to copy this song, lip sync, by NMR tones. And I thought about that a long, long time. How can we do this on a keyboard? All right. We must keep in mind the following. A standard piano, normally a full piano has 88 keys, and the lowest tone is A0 and the highest one is C8. Okay? Then on each piano we have this so-called tempered tuning. That means we have equal spacing, factor spacing between two half tones. And the formula that you can read everywhere is the following. The multiplication factor between two half tones is the 12th root of 2, which is this number. So we have to keep this in mind. Here again, a piano, the lowest tone, A0, with 27.5 hertz. The highest tone is C8, 4,100 something. And in the middle, we have the standard pitch, which we call in German the Kammerton, exactly at 440 hertz. How to simulate this? And I wrote a macro for our Chego 500, which looks like this. Might seem a little confusing. We have to excite all the tones from the lowest one to the highest one, and we have to record all these individual tones. And this is the macro that I wrote. So here's the factor spacing between the two half tones. We have 88 tones to record, 88, okay? And then from step to step, we have to multiply the carrier frequency by a factor of 12th root of 2 to get a new tone, which is basically higher in pitch. And this works. And so we end up with something which hears like this, or which sounds like this, very, very boring. So these are some of the individual tones from acetone, a single drop of acetone, which are recorded. You see it's a half tone difference. So the whole thing takes roughly 15 minutes to record a whole piano from the lowest to the highest tone. I've chosen only 4. Don't worry. Okay, so when all the tones have been recorded, we end up with something which looks like this, many, many tones. And to me, a very important experience was when you have such a software, don't forget to assign all these FIDs, because otherwise you will get completely lost. And so it took me a couple of days to get around this. And when you have assigned the tones, you are happy, basically. Now, each individual tone, each FID, has to be cut out and has to be stored individually on disk, 88 times. And one single tone, for example, looks like that. And now the next thing is to put it somehow on the computer. So I have bought a software which I actually like. It's from the Magix company, and it's called Samplitude, and it's very convenient. And so what has to be done is the following. This is the Samplitude software. We have different channels where we can put in some sounds. And then the next step is to pick up a software on the internet, which is free, and to use all the individual tones which have been recorded from the FIDs, and to assign them to the correct positions on the keyboard. I only take 4 of these 88 tones. And so on, and so on. So finally, we have assigned all the keys of the keyboard to individual NMR tones. That's the basic thing, the basic step. The next thing is to take a keyboard, which is able to play MIDI. And MIDI is a musical instrument digital interface. It means I can connect my keyboard to a computer. And this is done in this way. This is the software that we see on the screen. We have all the 88 tones here. And we take now the keyboard and link it via MIDI to our computer software. Okay, and now we make the following combination. We have the library of the 88 recorded tones. Okay. We have assigned all these 88 tones to the sound sampler, right? And now we can trigger all the tones by playing keyboard. And we can record individual tracks by using the software. And we can mix it in the end. And so we can play complex songs by using simple NMR tones. Okay, and I should emphasize, anything you will be hearing now to the very end of my lecture is only a tiny single drop of acetone, nothing else. Okay, the first demo, basically, how to do that. At home, I have my keyboard here, and the computer is here, so I can switch from here to here, and I simply switch the record button here, and I go to the keyboard, I play something. You see something happens here, okay? Something is recorded. It's just a quick and dirty demo, just to show you how it works. Now it's finished, and I tell the computer to keep the record. Okay, keep it, yes. And now we can play the tune. Okay, it works. Bingo. Now, this is an example of a record where 4 tracks have been used for the recording, a little more complex. And of course, we can manipulate the tones by using the software. There are certain apps, basically, which are built in the software where we can make the tone to sound like a guitar, for example, or to make it sound like a drum or whatever. And now the next song is the movie by Phil Collins, this Against All Odds, but played only with NMR tones. And watch it again. Anything is acetone, one single drop of acetone. And so we have to switch to the record here. 1 drop of acetone. Okay. You see, it works. And to go back to our slide, I'd like to show you a further example. And basically, this is one of my famous actors, Dan Fogelberg. And he has released a CD in 2003. And this is basically my favorite song. It's entitled Half Moon Bay. Sadly, Dan has died in 2007 from prostate cancer, but nonetheless, his music lingers on. Hope you have enjoyed the song as much as I do. So keep this in mind. 1 single drop of acetone. And I have a final song, also played by NMR tones. And this is dedicated to my colleague Tim Clark from the CCC. He became 65 in April. And it's a song by a group called Gary and the Pacemakers. And this song was released in 1964, and this was when I was 11 years old. I heard the song for the first time, and I was so fascinated by Ferry Cross the Mersey. You have to keep in mind, Liverpool is on the west side of England, and it opens to the Atlantic Ocean, and the Mersey River flows through Liverpool and is very wide. In the end, I think, say 2 kilometers or so. And those people who do not know this group, Gary and the Pacemakers, possibly anyone knows the famous song, You Will Never Walk Alone, which is played on soccer games, not only in England, but also in Germany. And it's the very same group. Gary Marston, the leader of this group, has composed a couple of beautiful songs, and this is my favorite. big fun to me playing around with NMR tones, my new hobby, to be honest. So, finally, I'd like to tell you, musicians, what does it mean? An acronym, and musicians stands for the following: multi-frequent utility for sound-inspired, crazy and insane abuse of new spectrometers. And when we translate this into German, it means mehrtonales Verfahren zum klanginspirierten, verrückten und blödsinnigen Missbrauch von neuen Spektrometer. Yo. Now, in the final end, I have to thank a couple of people. I have to thank Ty, who is from the Thomann company in Treppendorf, who helped me with all the media stuff and the sampling. Tom Fischer is a 19-year-old guy. Basically, he's the son of our secretary, Heike, and he's very skilled with all the media stuff, and he gave me many, many valuable hints how to use it. And my friend Chris Klepper, he had the idea for the next and final acknowledgement, this one. Acetone. Okay, so in the very end, I'd like to thank you very much for listening, and hope you have enjoyed the lecture and you have heard what NMR tones can achieve and how beautiful they might be, possibly. Thank you very much.